This video is part of the course Forensic Physics, How Science Solves Crimes in Court, presented by the Physical Sciences Consultorium. Throughout this course, we examine how the laws of physics are applied to forensic evidence and how scientific reasoning constrains legal decision-making in real investigations. In this episode, we turn to digital traces and sensor-based evidence. Modern crime scenes are increasingly data-rich, filled with recordings from phones, cameras, vehicles, and network devices. These digital traces are often treated as objective facts, yet they are physical measurements shaped by sensors, signals, and limitations. Digital evidence is not abstract information. It begins as a physical interaction. Light, sound, motion, pressure, and position are first sensed by hardware, converted into electrical signals, and then stored as data. Physics enters at the very first step of this process. Every digital sensor measures a physical quantity. Cameras measure light intensity, microphones measure pressure variations, accelerometers measure changes in motion, and GPS receivers measure timing signals from satellites. None of these measurements are direct representations of reality. Sensors operate by sampling the physical world. Continuous phenomena are converted into discrete measurements at specific intervals. This conversion immediately introduces limitations, because anything that happens between samples may be lost. Sampling rate matters. A camera recording at a low frame rate may miss rapid motion. A microphone with limited bandwidth may fail to capture short, sharp sounds. Physics determines what can and cannot be resolved. Resolution also matters. Digital measurements are quantized. They can represent values only within fixed steps. This means that even when data appears precise, it is always approximate. Smartphones are among the most common sources of digital evidence. They contain multiple sensors operating simultaneously. Accelerometers record motion, microphones record sound, cameras record light, and location services estimate position. Each of these sensors has its own limitations. Accelerometers saturate during sudden impacts. Microphones distort loud sounds. Cameras struggle in low light. GPS signals are affected by buildings and atmospheric conditions. CCTV systems are often treated as reliable witnesses. In reality, they are optical sensors with fixed viewpoints, limited frame rates, and compression artifacts. Motion blur and dropped frames can significantly affect interpretation. Wearable devices and vehicle sensors add further complexity. They generate continuous streams of data, but these streams depend on calibration, power state, and internal processing algorithms. A critical point must be emphasized. Digital data is not raw reality. It is processed information. Algorithms filter, compress, and sometimes modify signals before they are stored. Compression is especially important. To save space, digital systems discard information considered perceptually unimportant. For forensic analysis, this discarded information may be physically relevant. Another major challenge is timing. Digital evidence often relies on timestamps, yet device clocks are not perfect. They drift, reset, and synchronize imperfectly with networks. Two devices recording the same event may disagree on time. Without careful correction, this can lead to false conclusions about sequence and causality. Physics treats time as a measurable quantity, but digital systems treat time as a managed parameter. This difference matters greatly in forensic interpretation. Because of these factors, digital traces must be interpreted using physical models. Investigators compare recorded data with expected sensor behavior to test whether a proposed scenario is plausible. As in earlier episodes, uncertainty is unavoidable. Digital precision does not imply physical certainty. Apparent exactness often hides layers of approximation. Digital evidence is always affected by noise. No sensor operates in a perfectly controlled environment, and every measurement includes unwanted variations arising from electronics, surroundings, and signal transmission. Physics treats noise as an inherent part of measurement, not as a mistake. Noise can mask or distort real signals. In video, it may appear as grain or flicker. In audio, it may appear as hiss or background hum. In motion sensors, it may appear as small fluctuations even when an object is still. Filtering is often used to reduce noise, but filtering is not neutral. When a signal is smooth, some information is inevitably removed. This creates a trade-off between clarity and fidelity that must be acknowledged in forensic interpretation. Another major source of uncertainty is algorithmic processing. Modern devices rely heavily on software to interpret sensor signals. Motion detection, face recognition, and object tracking are not direct measurements but computational inferences. These algorithms are trained and tuned for everyday use, not forensic accuracy. Their outputs may be consistent, but consistency does not guarantee correctness. Physics reminds us that algorithms are models, not reality. False precision is a recurring risk in digital forensics. Numerical values, timestamps, and coordinates often appear exact to many decimal places. This apparent precision can be misleading if underlying uncertainties are ignored. Forensic physics insists on separating measurement resolution from measurement accuracy. High-resolution data can still be inaccurate if calibration or assumptions are flawed. Courts must be made aware of this distinction. Digital reconstructions often combine multiple data sources. Video, audio, and sensor logs may be merged into a single timeline. This integration can be powerful, but it also compounds uncertainty if synchronization errors are present. Clock drift between devices is a common problem. Even small timing offsets can alter the perceived order of events. Physics-based reasoning is required to determine whether such differences are physically meaningful. Another challenge arises from missing data. Sensors may stop recording, overwrite files, or fail during critical moments. Physics cannot recover information that was never measured. This limitation is fundamental. No amount of computation can reconstruct events beyond the limits of the data. Recognizing what cannot be known is as important as analyzing what can. In court, digital evidence must therefore be presented with restraint. Experts should explain how the data was generated, what assumptions were made, and where uncertainty enters the analysis. Visual aids are often more effective than technical detail. Diagrams showing sensor coverage, sampling intervals, or timing uncertainty help judges and juries understand limitations without requiring technical expertise. Forensic physicists play a critical role in this process. They translate sensor data into physical constraints rather than definitive narratives. Their responsibility is to prevent overinterpretation. Digital evidence does not decide guilt or innocence. It constrains what scenarios are physically consistent with the measurements. Legal judgment remains a human responsibility. This episode reinforces a central message of the course. Whether dealing with motion, heat, sound, or data, physics acts as a boundary on claims. It limits what can reasonably be asserted. Digital traces are powerful, but they are not infallible. Treating them as unquestionable truth risks undermining justice rather than supporting it. The Physical Sciences Consultorium is committed to explaining these issues clearly and responsibly. PSC aims to strengthen scientific literacy where physics intersects with law, technology, and society. If you find this course valuable, please like, share, and subscribe to support continued open access educational content. Your engagement helps sustain rigorous science communication. In the next episode, we will focus directly on uncertainty, probability, and expert testimony. We will examine how courts interpret scientific uncertainty and why honest limitations strengthen, rather than weaken, evidence.